Thanks a lot for the introduction and for the invitation. It's always a pleasure to give a talk to such a broad audience, and I'm really happy to be here again. And this is joint work with Natalia Garcia-Fritz, and this is about effective Mordell conjecture. So I will give an introduction to what it means for effectivity in the context of rational points, and then we will go into the actual theorem. Okay, good. So first of all, here was a problem in the classical setting, and the question was to come up with an algorithm that takes as input Diophantine equations, and the output is yes or no. Does it have a solution or not? And as we know, this was solved negatively, so such an algorithm actually does not exist. And this is after the work of Martin Davis, Hilary Putnam, Julia Robinson, and Yuri Matijasevic. Matijasevic last contribution to the problem was in 1970, and that finally solved the issue. And what about the rational numbers? Because after we know what's going on with the integers, we want to go to the rational numbers. And well, in this setting, the problem remains open. We want an algorithm. Well, we ask for the existence of the algorithm that decides whether or not our Diophantine equations have rational solutions. And well, there is an equivalent way to state this. Given an algebraic variety defined over Q, let it be affine or projective, and well, at least you have to consider affine. Is it true that we can decide for existence of rational points? And it makes sense to study this problem for smaller classes of Diophantine equations because the question is just too difficult. We have no idea what to do in this setting. And the first interesting case is varieties of dimension 1 curves. Okay. So by the way, if there is any question, yes, as it was said, please write the question in the chat or raise your hand. I'm happy to be interrupted. So curves. There is a trichotomy regarding rational points and curves. And in genus 0, the existence of rational points is a decidable question. There is the local global principle for quadrics. And if there is one rational point, we know that there are infinitely many rational points by an argument going back to the Diophantine. So basically, if you have a rational point, so you take your rational curve, your genus 0 curve, and you put it in the projective plane as a quadric. And then if you have a rational point, you pick this as a base point, and then you scroll with a line, and then you parameterize all the rational points in your genus 0 curve. So we know very well what's going on there. For genus 1 curves, story is a little bit more complicated. The existence of rational points cannot be tested by a local global principle, but we expect this to fail in a finite way. So there is a group measuring the failure of the local global principle for genus 1 curves. This is the Teichhafarevich group. And we expect this group to be finite. If so, then we can decide the existence of rational points on genus 1 curves. And if you have a point in a genus 1 curve, then you have an elliptic curve, a rational point, I mean, okay? You have an elliptic curve over the rational numbers. And for elliptic curves, we know that two things can happen. Either the rational points are just torsion, in which case you have finitely many of them, or the elliptic curve has positive rank, in which case you have infinitely many rational points. Deciding between these two is a different story, but I'm only concerned here about the existence or non-existence of rational points. And that, as I said, has to do with the Teichhafarevich group, as far as we know today. For genus at least 2, the story is different. We always have finitely many rational points only. This is a theorem due to Faltings in 1983. And the question is, can we decide for existence of rational points? Or if we get more ambitious, the question can be formulated as, can we find all of the rational points in your genus G curve? And I'm going to focus in this last case. Mordell's conjecture, and this was later proved by Faltings. The conjecture was formulated by Mordell in 1922 and was finally proved by Faltings in 1983. You take X, a smooth projected curve of genus at least 2, defined over the rational numbers, then the set of rational points is finite. By the way, I'm discussing only rational points over Q, over the rational numbers, just to simplify the exposition, but Most of what I'm going to say holds for number fields. You have to be careful with some technical points, but otherwise the story goes through. Okay, so right. So what I was saying is that if your curve has genus at least two, then the rational points are a finite set. And there are more proofs, not just Falking's original proof. There is also a proof by Vojta using Diophantine approximation in the language of Arakelov geometry. And this was put in classical terms of Diophantine approximation by Bombieri. And there is another proof more recently by Lawrence and Venkatesh that's somehow it has origins in the Falking's argument, but it's different. Okay, it's a more p-adic approach. Now I need to say something about height, just to fix the notation. The naive height of a rational number will be denoted by capital H, and is going to be the maximum in absolute value of the numerator or the denominator of your rational number, written with coprime integers. And this measures the complexity of your rational number. Of course, if you have a number that requires larger numbers, larger integers to be written down, then we say this is more complicated. And the logarithmic height is just the logarithm of the naive height. And you can think about the naive height as approximately of the same order of magnitude as the number of bits you need to express your rational number. And a basic proposition here, which is completely trivial, but nonetheless is extremely useful, is the Northcott property, which says that if you give me a bound for the height, then I'm left only with finally many rational numbers. And the proof is very simple, is that if you give me a bound for the height, then you give me a bound for the numerator and the denominator of your rational number. Therefore, you only have finally many of them. Okay. Now, you can do very much the same for rational points in projective space. So you take your rational point in projective space, and you choose coordinates in such a way that you get integers that share no common factor. So these integers will be uniquely determined up to plus or minus 1 sign. You define the height of your rational point, the naive height, as the maximum of these absolute values of the coordinates of your rational point. Now the logarithmic height is going to be the logarithm of the previous one, and again you can think about this as of the same order of magnitude as the number of bits you need to express your rational point. And in this way, every time you have a projective variety defined over Q, if you're given an embedding of your projective variety in some projective space, then we can talk about the height of the rational points of this variety. It's not uniquely defined because it depends very much on what is the embedding, but nonetheless, if the variety is projective, there is at least one such embedding. So we can have at least one notion of height and talk about this. And then the Northcott finiteness property holds again in exactly the same way. And therefore, if I give you a bound for the height of the rational points of your variety, then I can actually search for these points up to the height that you gave me, because I only have finitely many of those. I just need to try the different coordinates up to the given height. And this is connected to effectivity, because if you have a finite set of rational points that you want to determine, and you're given a bound for the height of this finite set of rational points, then you can just go checking up to the given bound for the height. And you don't need to go on checking forever. You just have something that stops when you reach the bound for the height. And this is what's going to be connected to effectivity questions. And the effective Mordell conjecture is going back to the previous question: can we decide the existence of rational points in the context of Mordell's conjecture? Or if I get more ambitious, can we find all of the rational points in this curve of genus at least 2? And of course, if I can find all the rational points, then in particular, I can decide whether or not there is at least one rational point. The other way around doesn't work, but I'm concerned with this stronger question. And the conjecture is that given a smooth projective curve defined over Q of genus at least 2, and a choice of logarithmic height in this curve, then there is some effectively computable number, capital B, that depends on the curve and depends on the chosen height, so that every rational point has height up to this bound only. And well, if you know this number capital B, then searching for the rational points is just a finite computation. You just take the tuples and plug them into the equation of the curve and go checking. I'm not saying this is efficient. I'm just saying this is effective in principle. Now, if you can give me such an algorithm that's moreover efficient, much better. But the conjecture is about effectivity only. And you can get more ambitious. There is a stronger version of the conjecture, which is written below the equation here. It says that maybe if I fix the genus and my height is canonical in some sense, then the height of the rational points can be bounded linearly in the logarithmic height of the curve. So the logarithmic height of the curve can be thought as the Faltings height of the Jacobian, or if you prefer something in more elementary terms, you write down equations for your curve, and they have coefficients, and you keep the height of those coefficients, the logarithmic height. So one can expect that the logarithmic height of the rational points of the curve, they grow at most linearly on the logarithmic height of the coefficients of the equation defining the curve. Now, this conjecture is very deep. So for instance, this last version of the conjecture implies the ABC conjecture. If you apply just to the Fermat degree 4 curves, for Fermat degree 4 curves, you have effective Mordell, then you get the ABC conjecture. So it's difficult. It's a difficult problem. Then, well, one can always get more ambitious, right? So I can ask whether, given a Diophantine equation in many variables defined over Q, and I put some comparison of height conditions, like for instance, the first coordinate, I want it to be simpler than the second coordinate. So the height of the first coordinate is less than or equal to the height of the second coordinate. Conditions of this sort. So I get my Diophantine equation with a bunch of conditions comparing the heights, and I can ask, can I decide for the existence of a rational solution satisfying all these conditions? And effective Mordell is something like this, because in effective Mordell, when you ask the effective Mordell conjecture, you are concerned about the existence of solutions whose height is controlled by the height of the coefficients. And you can vary the coefficients and see them as another variable. So this version of the problem contains the effective Mordell conjecture. But this is too much to ask for. So it turns out that this problem is undecidable. We proved this with Natalia Garcia-Fritz and Xavier Vidot well, 2 years ago, but yeah, it's coming up this year. It's on the archive, by the way. And yes, so in this generality, the question of effectivity is undecidable. So we better stay with a simpler case of curves, because in this setting, we can expect to have an answer, a positive answer maybe. Now, there is something else you can ask, effectivity for the number of solutions rather than the complexity of the solutions, the height, just the number. Well, imagine that you have a machine that you enter your equations for the curve, and the machine will output a number, and this number is the number of rational points. It will not give you the rational points, just the number of them. Well, if you have an oracle like this, then actually you can find the rational points. You just search one by one and in the ambient space and plug the coordinates into the equation and check whether or not your point is on the curve. And you will find points until eventually you find all of them. And you know you have all of them because you're matching the number of points that the oracle is giving you. But this is too much to ask for. So far, the only thing we have are upper bounds for the number of rational points. And these upper bounds, especially they come from Boita's proof, although I'm going to mention some other theorems that are related to the question of bounding the number of rational points. And that's not good enough for effectivity, because even if you know a very explicit boundary, like for instance, this curve has at most 3 rational points, and you start searching for rational points and you find 2 of them. Question, will you ever find the last one? or there is no third rational point. So, well, we don't have a way to tell. So knowing an upper bound for the number of rational points is, as far as we know, is not enough for effectivity, for finding the rational points. Before Falting's theorem, we knew some stuff about Mordell's conjecture. Some results are listed here. I'm not claiming this is everything we knew, but these are some landmark theorems before Falting. First, there is Chabauty's p-adic method. If the rank of the Jacobian, so J sub x is going to be the Jacobian of my curve. Some abelian variety associated to the curve. If the rank of the Jacobian is strictly less than the genus of the curve, then it turns out that Chabauty proved that the number of rational points is finite. And I'm going to say a bit more about this. And the method is completely p-adic. It's not something about heights. Heights are global. They consider the contribution of all primes and even Archimedean, but this is a local method. Then in 65, there is a theorem by Mumford coming from certain height inequality. So this is global. This is about heights. And this is known today as Mumford's gap principle, which says, roughly speaking, that the rational points of X are very sparse. Okay, they are very sparse. If you count by height, you get very few of them as the height bound increases. Of course, we know today that there are only finitely many of them, but by that time, that was not known. So it was new information to know that these points are really sporadic. They show up every now and then, but very far from each other. And then there is the Demyanenko-Manning theorem that says that if your curve admits n in the linearly independent maps into some abelian variety A, and this abelian variety has small rank, what does that mean? That the rank of the abelian variety is strictly less than the number of maps that we're talking about, then in this case, the rational points of the curve are a finite set. And this says a bit more. In principle, they are effectively computable. This comes from the proof of the theorem. So in principle means that you need to go through the proof and keep track of all the choices of heights, because this is a proof based on height theory, and how to translate linear equivalence of heights into height comparison. And well, I don't think anyone has worked out what comes out of the proof in this generality. And I don't think that's going to happen anytime soon, because it's rather complicated to keep track of all of that. In any case, it is effective in principle. And after Falting's, these theorems are still alive. So the Mumford gap principle has many applications today. For instance, it shows up in the proof of Mazur's conjecture regarding the number of rational points in curves by several authors, some of them in this audience. And but I'm going to talk about Chabauty's proof. This was revisited by Coleman in the 80s, and it gave an effective bound, for the number of rational points, provided that you have this rank condition. And the theorem is this: if you take a smooth projected curve of genus at least 2 defined over Q, and some auxiliary prime, which is not too small, is bigger than twice the genus, and the prime has to be of good reduction for your curve. So you take the curve mod P, and still the curve is smooth. Now we have this Chabauty condition that the rank is strictly smaller than the genus. Then the number of rational points is less than this quantity. So what is this quantity? You take the curve mod P and count the mod P points. Of course, this is finite, and you can count. And then you take the geometric contribution coming from the canonical divisor. This is 2G minus 2, where G is the genus. By the way, this number is the degree of the canonical divisor. And you get this completely explicit bound for the number of rational points. And the bound is so good that in some cases you can match it by finding rational points, and then you know that you got all of them. However, that's not the way to use this theorem. You go into the proof, it goes by p-adic integration, and you use that kind of argument to find the rational points. And in practice, it works quite well whenever this rank assumption is satisfied. I'm not claiming that it works in every single case, but it works very well. And you can deal with many curves in this way. The problem is that we don't know if this process terminates. So we don't know if this process is in fact an algorithm, even under this rank assumption. There are conjectures regarding the Mordell evasive that would imply that the Chabauty Coleman approach terminates, but we don't know that today. And the same comments apply to non-abelian extensions after Neon Kim and Jennifer Balakrishnan and many other people. So they work very well in concrete cases, but we don't know for sure if those algorithms terminate. Well, something else I want to mention is that Gerson Caro and I extended the Chabauty Coleman bound to surfaces. This was my previous talk in this seminar a few years ago. Time flies. It was some time ago. Yeah. And well, Balakrishnan and Caro recently, very recently, maybe 2 weeks ago, 1 week ago, I'm not sure, they posted a paper in the archive where they revisit this method for surfaces. They improve the method, they get better bounds in some cases, and they use this method to find actually the rational points in certain surfaces. So I find that new development quite amazing, and by Balakrishnan and Caro. At least when Caro and I proved this bound, we thought, okay, we're happy that we got a bound. It's very explicit, looks like Chabauty, but we didn't expect this to be, we didn't expect it was possible to modify this argument to make it work in concrete cases, but it turns out that Caro and Balakrishnan made it work. Now, the other thing I mentioned was the Demyanenko-Manning theorem, that for some reason is usually called the Manning-Demyanenko theorem, although it's not alphabetical order. Let me state it very explicitly. You take a smooth projected curve of genus at least 2 defined over the rational numbers. If the curve admits n linearly independent maps into some abelian variety defined over Q, and this abelian variety has small rank over Q, meaning that the rank is less than the number of maps, then the rational points are a finite set, and in principle, this is effectively computable. This proof is using heights, it's not p-adic. This has been made explicit in some cases when the abelian variety we're talking about is an elliptic curve, dimension 1, of small rank. And there are a number of authors, most recently I would say that Biada and collaborators have pushed this setting farther, and they have very explicit results when the abelian variety is an elliptic curve, always under this rank assumption. Okay, so this is something getting closer to effective Mordell, even though it's a restricted case. It's quite amazing what can be achieved by this. Well, there is another approach to effective Mordell using modularity. Some years ago, 2011, Ramurthy and myself gave a new effective and explicit proof of finiteness of solutions to the S-unit equation. Of course, the S-unit equation involves S integers, not rational points. Our proof used a modularity of elliptic curves, bounding the congruence number, and that involves congruences of modular forms. And our height bounds are small enough to be practical. So they can actually be used to find the solutions of S-unit equations, although they are far from what we conjecture. This was worked out in some other cases by several authors, including Rafael von Kannel. He worked in this extending this bound for other Diophantine equations. And very recently, Alpugi used modular forms in a similar way to prove the effective Mordell conjecture for some curves, including, as a special case, this very explicit family that you have here. That's really amazing that you can deal with such a large one-parameter family of curves and get effective Mordell. Now, unfortunately, the bounds that the height bounds that Levent got are not explicit and they are not practical. But nonetheless, from a theoretical point of view, this is a very interesting development. using modularity. So here's our theorem. This is the vague formulation of the main result. This is joint work with Natalia Garcia-Fritz, and it's going to be posted on the archive sometime next week. And after the talk, please, if you have comments, let me know, even during the question part of the talk at the end or by email. So I will try to include your comments into the final version of the paper. You take a smooth projected curve over the rational numbers of genus at least 2. If the curve has enough automorphisms with respect to the rank of the Jacobian, then the effective Mordell conjecture holds, and we get an explicit and practical bound for the height of the rational points. Now, of course, this is not a good formulation of a theorem. You need to make some points precise. First, what do we mean by enough automorphisms? And it turns out this has to do with spherical codes, sphere packing. Secondly, what is the height that we are using? Because I say we can bound the height of the rational points, but what is this height? And then finally, the height bound. Of course, I claim this is explicit, but well, then I should write it down if it is explicit. It's not. So it's fine to say, from a theoretical point of view, it's fine to say there is some effective bound, even if you don't write it down. But if I want to apply this in some example, I better write down what the bound is. And we're trying to do that in the remaining part of the talk. So first, let me try to explain what enough automorphisms mean. And for this, I need to say a little bit about angles in real vector spaces. Given a set of n different unit vectors in r to the power r, in the real numbers to the power r, alpha u is going to be the least angle between two different vectors in this set. And then I'm going to define theta rn as the supremum of these minimal angles as you vary your configuration of endpoints. So for instance, theta 2n concerns endpoints, n unit vectors in the real plane, because r is equal to 2 here. And when you have these unit vectors, there's going to be a minimal angle. And you want to maximize this minimal angle. What is the configuration? The vertices of an n-gon. That maximizes the minimal angle. And therefore, the regular n-gon can be used to compute this theta rn in the case r is equal to 2. But in general, it's difficult to compute this theta rn. That's an open problem. You can approximate it. There are good upper and lower bounds in practice. This is the theory of spherical codes, quite an active area of research. And conveniently, there are ready-to-use bounds, and even in many cases, even exact values for this theta rn in this web page maintained by Henry Cohn, sphericalcodes.org. Good. So what do we mean by enough automorphisms? You take a genus V at least 2, a number little n at least 3, and tau is going to be defined as cosine of the previous angle minus 1 over g if r is at least 2, or just 1 minus 1 over g if r is equal to 1. So when the curve x has genus g and the Jacobian has rank r, I'm going to say that we have enough automorphisms if taking little n as the number of automorphisms. This tau parameter is strictly positive. So the definition may look a little messy, but you can compute everything here. So for instance, what is the simplest case when the Chabauty Coleman approach does not apply? Genus 2, rank 2, because then the rank hypothesis is not satisfied. And in this setting, I can vary the number of automorphisms, the potential number of automorphisms of the curve, and see what is the number tau. You get negative up to 6 automorphisms where you get 0. So tau becomes 0 when you have 6 automorphisms. But when you have 7 or more automorphisms for your genus 2 curve, then tau is positive. And therefore, for genus 2 and rank 2, enough automorphisms means at least 7 automorphisms. Okay, so this is from the theory of spherical codes, and this is what we use to define what enough automorphisms means. So here's again the theorem, a little bit more precise. You take your curve, genus G, rank R, and little n is the number of automorphisms. If tau is strictly positive, then we get effective Mordell. And there is going to be an explicit and practical bound for the height of the rational points. I still have to explain what it means. So what is the height that we're going to use? And what is this height bound, the mysterious height bound? Well, it turns out that the mysterious height bound is given in terms of Arakelov theory, Arakelov theoretical invariance. I'm going to get to that point. I think there is something in the chat.
Yes, Michael Stoll asked if the automorphisms are defined over Q or over Q bar.
Oh, yeah. So I tried to, I tried to make that implicit in the notation. So X is defined over Q, and I'm not extending scalars. So yes, this is defined over Q. Okay, I'm not extending scalars. It's really automorphisms of the scheme over Q. Okay, thanks for the question. Yeah, that's something that needs to be explained. Now,
as a follow-up question for myself, if you have large automorphism group over Q, does that somehow affect also the rank because you can use the automorphisms?
It could, in principle, affect the rank, but for instance, we have examples of rank 2 with 12 automorphisms. So then automorphisms, you can get many automorphisms and small rank. But one can, of course, analyze to what extent more and more automorphisms will increase the rank. But it's not necessarily the case that the rank will increase drastically when you have too many automorphisms. The example I mentioned of 12 automorphisms and rank 2 is for genus 2. It's not something too complicated. Okay. Yes, so thanks for the question. Yes, these automorphisms are of X, not X extended scalars to Q bar. Yes, so yeah, I still need to explain what is the height and what is the height bound. Now, there is, of course, when you have a curve, a good tool to analyze the curve is the Jacobian. And we're very used to the idea of picking a rational point and use this rational point to embed the curve into the Jacobian in this way. But there are two issues with this construction. One issue is that you may fail to have rational points. We don't know that in advance. So this P0 does not need to exist. And secondly, how does this map and all constructions that you're going to make using this map depend on the choice of the base point, P0? So for our purposes with Natalia, we don't want to deal with these two issues. So we sacrifice the word embedding this condition, and we get a finite to one map, and this map is completely canonical. The map takes the canonical divisor class minus 2G minus 2 point. Okay, and the point is what you're mapping. And now, of course, this is a degree 0 divisor, so it gives you a well-defined point in the Jacobian. And this map is what we're going to use to map the curve to the Jacobian. It's not an embedding in general, but it's good enough for defining heights. And now in the Jacobian, there is a canonically attached divisor class, capital theta, the theta class. It's sample and symmetric, and for technical reasons, I'm going to be using twice this class, not the class itself. And attached to it, there is the Néron-Tate canonical height on the Jacobian, associated to the Jacobian, and the divisor class twice theta. This height is very good. It's really convenient and has some properties. First of all, it's canonically defined. There is no error terms or choices involved. Is what it is. Okay. It satisfies the Northcott property. And when you consider the Mordell-Bell group, the rational points, and you extend scalars to the real numbers, well, you get a real vector space. And on this real vector space, you can extend this height function and get a positive definite quadratic form. And after you have a real vector space with a positive definite quadratic form, you get a notion of geometry. You get angles, inner products, norms, all of this Euclidean geometry. And we're going to use that using the net-on-Tate height on the Mordell veil real vector space. So here's our theorem again. We take a smooth projected curve defined over Q of genus at least 2. Little r is the rank of the Jacobian. Little n is the number of automorphisms defined over Q. If the invariant tau coming from spherical codes is strictly positive, then the effective Mordell conjecture holds. There is an explicit and effective computable bound capital B, depending only on the curve, that satisfies that the canonical height of J of P, so you map the point canonically to the Jacobian and take the net-on-Tate height. This height is bounded by this capital B for all rational points. Okay. So I still need to explain what this capital B is, but at least we know what enough automorphisms means, and we know what is the height we're using. By the way, I think I have like 1 hour, right? Yes, okay. Okay, thanks. Yes, so still some time left. Now I need to explain these Arakelov theoretical invariants that are used to define the capital B bound. So in his Arakelov geometry paper in 1984, Partings introduced a new, well, he did wonderful things there, but in particular, he introduced a new invariant attached to a compact Riemann surface, and this is called delta, the delta invariant of Partings. The actual definition is rather complicated. I'm not going to explain it here, but there is a way to think about this. You take the moduli space of compact Riemann, in the course moduli space of compact Riemann surfaces of genus this one, and associated to your Riemann surface, there's going to be a moduli point in this space. And you can try to measure what is the distance of this moduli point to the boundary of your moduli space with some compactification, okay? And well, you take that distance and you take minus logarithm of the distance. Meaning what? If the point is very close to the boundary, then the distance is small, and therefore the delta invariant is large. Okay, so the delta invariant is like the proximity to degeneration of your Riemann surface. And it looks like it depends on the compactification and the metric that we are choosing for the moduli space, but the actual definition given by Partings does not depend on anything. It is what it is. Okay? Here's a picture. This shape is my moduli space. Here's the moduli point associated to the Riemann surface Y. The red curve here is supposed to be the boundary of the moduli space, and I take the distance to the boundary, okay? Minus logarithm of this distance is precisely the delta invariant of Partings. Now, that's a definition that's purely analytic. And now I need to give a definition that's purely arithmetic. In Arakelov geometry, you start with a curve over Q of genus at least 1 if you want. And after clearing the denominators of the equations, plus some geometry, algebraic geometry, one ends up with a minimal regular model over the integers. And this is curly X is going to be a surface in the sense of scheme theory. And this surface is fibered over the prime numbers. It's also necessary to add metrics in the complex points of the curve. That's a different story. And some related Archimedean objects like measures and vector boundaries with metrics and well. Now it makes sense to reduce your curve modulo P because you clear the denominators. I think there is another question in the chat.
Yes, would you please unmute and ask away?
Yeah, there are formulas. Yes. There are explicit formulas for in terms of different choices of coordinates on the modular space, in particular this one. And there are explicit formulas for the delta invariant. And you can approximate it numerically to whatever precision you want, provided you can deal with these ugly formulas. But yes, I think that recently Wilms has some theorems regarding how to do this numerically.
Okay, thank you.
Thanks for the question. Yeah. Good. And now, since I clear denominators, or since I have a surface fibered over the prime numbers, I can reduce mod P. When I reduce mod P, I end up with a curve over FP. Now, this curve could be smooth, and in fact, most of the time it's going to be smooth, but sometimes, in finally many cases, it can be singular. You get a singular curve. And Natalia and I, for our purposes, we needed to define an invariant that's going to measure how complicated these singular fibers are. And this definition only uses linear algebra in terms of the intersection of the different components of the special singular fiber. And this is what we call phi p of x. So, for instance, one case that's convenient is when the special fiber, the reduction mod p, is irreducible. Even if it's singular, being irreducible implies that our invariant is 0. I'm not going to define it, but at some point I will show you numbers, okay? Here's a picture. This surface is spreading out the original curve x. This Riemann surface is the complex points of the curve, but then you can reduce mod 2, mod 3, mod 5. Now in this picture, the first curve is irreducible, but it is singular. The second curve is supposed to be smooth. This is over 3, reducing mod 3. Reducing mod 5, you get something singular, but it's no longer irreducible, has many components. So in the first case, our phi invariant is 0, and the second case is also 0, and the third case is going to be some larger number because this is more complicated. Okay, now let me put together the Faltings delta invariant, which is analytic, our phi p invariants, which are arithmetic, and the genus, which is geometric. And you put all of this together in this formula, and that's what we call capital M. Now, given a fixed genus, this is going to be linear on the delta invariant, linear on the phi invariants, and there is this additional junk coming from the genus. And the formula is a bit messy, but you can imagine that if you can compute the delta invariant, then you're done, because these phi p and they are really easy to compute. You just compute the special fiber, and this is even programmed for some curves. And then you do some linear algebra with intersection matrix, and then you get the phi p. Good. So it's ugly, but it's not too big. It's linear in the relevant invariants. And the formula, although it's a bit messy, one can compute it, or at least give an upper bound for this capital M. And finally, here's the theorem. You take X, a smooth projected curve of genus at least 2. Little r is the rank of the Jacobian, little n is the number of automorphisms. And if the tau invariant coming from spherical codes is strictly positive, then every rational point with trivial stabilizer with respect to the automorphism group satisfies that the canonical height is bounded by this invariant capital M divided by 2g times tau, the same tau that we had from spherical codes. And this makes sense because tau is positive. Okay, so this is the theorem. It's very explicit now. For this, to prove this, we need an explicit version of Mumford gap principle, which is this theorem. Looks ugly, but what it's saying is that you get height inequality for the rational points. And this height inequality, when you work out what's going on here, at the end, it's telling you that there is some repulsion principle for the rational points coming from the curve. So you take your curve, you look at the rational points, map them to the Jacobian, and these points will repel each other. Okay, this is what's encoded in this ugly inequality. So this is happening inside the Jacobian. You map the rational points with J to the Jacobian, and then you get this expression. By the way, these brackets here mean the inner product in the Mordell veil space using the quadratic form coming from the height, the Néron-Tate height. And you can divide here by the height and get this expression. Now the inner product, as you know, has encoded into it the cosine of the angle. I think there is another question.
Yes, concerns genus 3, what the minimal value is for the number of automorphisms for which your theorem applies, for which tau is positive.
Oh, I don't actually remember. Sorry, I don't remember. After the talk, I can check in the tables of spherical codes and give the answer to you. But I remember it was not too big. But yeah, sorry, I don't remember the number right now. But yeah, sorry about that. But as I mentioned, this is explicit. I can just go to the tables and check what's going on there. It's all numerical. Okay. Yeah, sorry, my answer was not satisfying. Okay. Okay. Oh, by the way, yeah, something I should say is that if you fix the rank, the larger the genus, the smaller the bound. So larger genus helps. So I don't remember the number, but I can tell you that larger genus helps because the genus is here. So if you get a large genus, 1 over G is small. And then you're subtracting a smaller number, so you have better chances for this to be positive. Yeah, sorry about that. Yeah. Okay. Yeah, live broadcasting, so things can happen. Okay. Yeah. So yeah, I was saying that this inequality at the end is telling you an upper bound for the cosine of the angle separating the points. Okay. Now there is this m here. If it were not for this m, this is a theorem of Mumford. Okay. Now, the theorem of Mumford had some error term that's not precise, and several authors for different purposes made this term more precise, but it was not enough for our purposes. So we had to do some Arakelov geometry to get a very concrete expression for the error term in the Mumford inequality. And this m is this m, the same one, coming from analytic contribution, arithmetic contribution, and geometric contribution. Should not be a surprise because it's coming from Arakelov geometry that's mixing everything up. Yeah, so the whole point is that in Arakelov geometry, there is a relation between the intersection Arakelov pairing and the Néron-Tate height. And this is a theorem by Faltings and also by Hryljak. Okay, I'm not giving the proof of this because it's complicated. Actually, this is where the magic happens. Okay. But let me analyze what this inequality is saying. Let's go to the extreme case when the two rational points have the same height. When they have the same height, these fractions become 1. So you get 2 divided by 2g. This square root disappears, and the cosine of the angle is bounded by this very simple expression. You move 1 over g to the other side. You move the height to the other side, and you get, so the height is positive, so you can multiply by it and still get the inequality in the same direction. And you get this bound. So this is starting to look good because we have the height is less than something, okay? But of course, this is very special, is when the height of the 2 points is the same, and we have no idea what's going on with this angle cosine theta. So let me deduce the main theorem out of the Mumford-Gauss principle that we had so explicitly. You take a point with trivial stabilizer and let the automorphism group act on it. They are defined over Q, therefore you get a bunch of rational points. How many? As many as the size of the automorphism group, because the stabilizer is trivial. The canonical divisor class is stable under automorphisms, and the theta divisor is also stable under automorphisms. And therefore, we get that the height of these points are the same. All of them have the same height inside the Jacobian. Now, there are 2 points that minimize the angle. And these 2 points that minimize the angle, they will be, there's going to be an upper bound for this angle coming from spherical codes, because spherical codes will maximize the minimal angle. So you get the bound in this order. And when you take cosine, you get the bound in the other direction. And therefore, the cosine I had in the previous slide, coming from the angle of 2 points, is larger than this tau. You take cosine minus 1 over g is larger than this tau invariant. So the m from the Mumford-Gauss principle divided by 2g is larger than tau times the height of the point. Now, if tau is strictly positive, you can divide by tau, and you get the theorem. Just that, okay? And you get a bound for the height of the rational points that have trivial stabilizer. Now, of course, those that have non-trivial stabilizer, you can compute them. It's just solving some equations coming from the automorphism group. Good, and in this way you get the theorem, you get this bound, where m, let me remind you, m is this very explicit expression. Now, as a proof of concept, let me run this theorem over a complete example. I'm not claiming this example is new. In fact, it's not new. It's a very interesting curve because, in my opinion, it seems to be the simplest curve of genus 2 and rank 2, which is something we want because it's not covered by Chabauty, with enough automorphisms. Enough automorphisms in this setting was at least 7 automorphisms. And okay, now I remember, at least 6 is for genus 3. Yes, now I remember. Okay. Yeah, so, right. So in this case, we have 8 automorphisms. You think for a second, you will easily find them. And tau is going to be positive. Now, there are many ways to compute the rational points here using Manin-Demyanenko or maybe non-abelian Chabauty. There are ways to do that, but it's not the point. I'm not claiming this is a new curve. I just want to see the theorem working explicitly in a concrete example, just to tell you that things work out. Okay. Now, the only bad prime is p equal to 2, and one computes that our invariant measuring the complexity of the bad fiber is 4. And this is a linear algebra problem with this matrix. This is the intersection matrix of the special fiber. And has some structure. You have these numbers in the diagonal. They are self-intersections of a special fiber, therefore they are negative. And off the diagonal, they meet transversally, so you get only zeros and ones. Now, what about the delta invariant? We don't compute it, we bound it using the arithmetic Noether formula that will relate the delta invariant to the Faltings height of the Jacobian. And the Faltings height of the Jacobian is something you can approximate very easily using differentials. You integrate differentials and you get the Faltings height of the Jacobian. So at the end, one does the computation, and this capital M turns out to be less than 103. Now, in this case, you plug in the numbers. Tau was at least 0.2, not too small, actually. And 2G is 4, and you do the computation, and you get basically 130. Okay, 130. That's going to be a bound for the height of the rational points mapped to the Jacobian. And now Michael Stoll proved a comparison that has been improved since then, but proved a comparison between the Néron-Tate height and the naive height of the rational points. So the logarithmic naive height is going to be less than 67. Okay, when you do the comparison between these two heights. And therefore, when you take the naive height multiplicatively, not taking logarithms, it's bounded by 10 to the power 30. This number is huge, okay? But it's not so huge. So there are techniques to find rational points up to bound like 10 to the power 1000, for instance, okay? So this is well within the range of computation using the Mordell Veil sieve to bound, and this has been developed by many people here, and it's amazing how far they can get with the computation using the Mordell Veil sieve. And yeah, so at the end, what you get out of this is that this curve has only these 8 rational points, the 2 points at infinity, and these other points that are the obvious ones. You look at the equation and you immediately find these points. And there is nothing else. Now, the paper, as I mentioned, is going to appear next week if everything goes fine. And if you have comments, corrections, suggestions, complaints, please let me know. Send them to us, and we will be happy to review the work in order to include your comments. And thank you very much for your attention.